Last time we considered so-called closed sets or classes of Boolean functions, where the closure of Q equals Q. Let us recall that the closure of Q is just the set of all functions you may compute via a Boolean circuit over the set Q as the set of your basic functions. So, which functions you can obtain from functions in Q with a Boolean circuit? Okay, and so far we have considered the following closed sets: T, the set of all Boolean functions; this bottom set of all projectors; the set of all functions preserving 0; the set of all functions preserving 1; and the set of all self-dual functions, that is, functions that equal the dual. This is a set of all such Boolean functions for which the following equation hold. If you take this function at x, the result will be the same as negating the value of this function at not x, where not x stands for coordinate-wise application of negation to coordinate-wise negating of arguments. Now, let us introduce two more classes, which will be proven to be closed. First of all, the class of monotonic functions. What does it mean that a function is monotonic? A function is monotonic if it preserves or respects some ordering. But which order can we have over arguments of our functions? Look, a Boolean function, is a function from tuples of zeros and ones to just zeros and ones. Which order can you impose onto these tuples? How can you compare them naturally? In fact, the main idea is as follows. So assume that we have two tuples of length, say, 4. Which one is greater? Which one is naturally greater? It is quite reasonable to assume that the rightmost tuple is greater. Why is it greater? Because it has a greater coordinate at one of the positions, where all the other positions are in fact equal. Of course, if we replace all zeros with ones, we will obtain even greater tuple. But this order is essentially non-linear. Okay, if we try to compare these two, what can we say? We see that with respect to the second coordinate, the right one is greater than the left one. But with respect to the third coordinate, the situation is reverse. So, in fact, neither the left-hand side is less than the right-hand side, nor the right-hand side is less than the left-hand side. So, these are incomparable. This is the idea, but now we can give a rigorous definition. An order on the set of our tuples. we will define the non-strict version of this order, and the strict one is its obvious counterpart. So I say that, assume that we have two tuples of one length. So these are two tuples. Then by definition, x is less or equal than y, if and only if at every coordinate xi is less or equal than yi, in where this order is just our natural order on the set of naturals on its subset where 0 is less than 1. I mean this order here. This is exactly what we have. It is easy to observe that its strict counterpart, which is what? When one tuple is strictly less than another one. By definition, that means that it is less or equal, but not equal. We can easily prove that. That means that there exists some set I, which is not empty, the set of indices I, such that for every index from I, xi is 0, which is less than yi, which is 1, and for every j absent from this set I, xi equals xj equals yj. So somewhere the first tuple has zeros, while the second one has ones, and at all the other positions their coordinates are equal, as we say have here. Comparing these two tuples, you may take 2 and 4 as our set I. Okay. It is easy to see that this relation is indeed a non-strict ordering. It is an exercise. So now we can define the set of monotonic functions. A function is called monotonic if and only if it takes greater values at greater arguments. So for every two tuples sigma and tau, if sigma is less or equal than tau as a tuple, then the value at sigma is less or equal than the value at tau. That's it. Okay. A few examples. Our first example is, say, conjunction. Conjunction is monotonic, and disjunction is monotonic. Why is it so? It is easy to see that. Let us depict our ordering as a diagram. So 0, 0 is strictly less than 0, 1, 0, 0 is strictly less than 1, 0, and both these tuples are strictly less than 1, 1. So a function is monotonic if and only if it doesn't take it doesn't have any unity. It doesn't take value 1 at an upper point. It doesn't take value 0 at an upper point than any point where it takes 0. So it has no zeros upper than any unity. So for disjunction we have 0 here is a value, 1 here, 1 here, 1 here. Clearly it is monotonic. So every unity, every 1 is upper than every 0. At least there is no 0 greater than 1. So it is monotonic. The same for for conjunction. For conjunction, we have zeros everywhere except the greatest point 1, 1. Here we have unity. Still, no 0 is greater than any unity, so it is monotonic. Let us consider an example of a non-monotonic function. Say addition. Addition is not monotonic. Let us demonstrate it. In fact, we need just two tuples in order to break monotonicity. So here we have 0 plus 0 is 0, 1 plus 0 and 0 plus 1 is 1. Everything is okay up to now. But here we have 0. So we see that this tuple is less than 1, 1. But nevertheless, 0 plus 1, which is 1, is greater than 1 plus 1. So it is, in fact, not monotonic. Clear negation is also not monotonic. And as an exercise, you may prove that our majority function is monotonic. It is almost obvious because this function gives this function of 3 arguments gives us the value the majority of its arguments take. So if you add some unities, if you replace some zeros with unities, then the value of this function may get just greater. That's it. And in fact, the class of monotonic functions is closed. So it is sufficient to prove that its closure is included into M. So by induction, we need two things. If we know the drill of our last lecture, we need just two things. Every projector is monotonic, and that monotonicity is preserved via a superposition if some function is obtained from a few monotonic functions this way, if H and all our G's are monotonic, then the resulting function F must be monotonic as well. Let us check these two things. The first one is almost obvious. So if we assume that sigma is less or equal than tau, then clearly, if we take some projector, it returns us sigma I at this tuple sigma, which is, by the definition, is less or equal than tau I. It's obvious. And now, for superposition, as usual, we let sigma be less or equal than tau, then what is f of sigma? F of sigma is h of g1 of sigma, and so on. But every such value is less or equal than the respective value at tau. So that means that this whole tuple, this entire tuple, is less or equal than this one. Hence, as H is monotonic, here we, of course, had a reference to the fact that every Gi is monotonic. As H is monotonic, here we will have H of this greater tuple, which is f of tau. That's it. So this proves that our class, the closure of M is included in M, hence the closure of M equals M. This class is closed. It is a closed set of Boolean functions. And the last closed set we need will be that of linear functions. The definition is quite obvious, and now we will need no proof of this class being closed. By definition, L is the set of all functions you may compute from plus and unity, where unity is just a constant one with one argument. So this function with one argument returns us 1 given 0 or 1. It is a constant 1. So this is called the set of linear functions. Why are they linear? It is quite obvious that every such function is the sum of its arguments plus maybe 1. I will not give you a formal proof. It is quite clear that if you apply plus and unity as a result, you will obtain just a sum of arguments of our function plus maybe 1 or maybe just 0. Why is it so? It follows from the following fact. First of all, x plus x, say if you have, it follows from commutativity, associativity, and and nilpotence of our addition. So it is commutative, it is associative, so you can freely change the order, regroup your summands, and moreover, x plus x is always 0, while 0 may be always ignored. And of course, 1 plus 1 is still 0. Yeah. Which functions are linear? It is quite easy to prove that a function is linear. You should just you just have to show how you can compute it using addition and 1. Of course, plus is linear. Of course, constant 1 is linear. Constant 0 is also linear. Why is it so? As 0 of x equals 1 of x plus 1 of x. So it is obviously linear. What else? Negation is linear. It is quite important to notice because not x is just x plus 1. What else? In fact, neither conjunction nor disjunction nor majority are linear. Every projector is of course linear. It is easy to see because for every projector we have this equation by definition. So the right hand side is linear. So every projector is clearly a linear function. We need not any proof that this set is closed. We know that the double closure of any set is the same as it's just singular closure. So the closure of our class L is just this class itself, so it is closed. It is obviously closed, but it is not obvious how can one prove that some function is not linear. So, by definition, a function is linear if you can compute it this way. But how can you prove that a function is not computable? Why such a circuit? So how can one prove that, say, conjunction is not linear? Why is it so? How can you prove it? Okay, let us develop a little more theory to do so. First of all, I will tell you about some special representations of Boolean functions. You may think of them as circuits of some special form. First of all, this is a DNF, a disjunctive normal form. What is it? Informally speaking, it is expression of the following form. You take some variables, maybe with their negations, and apply conjunction to them. Then you take a few such conjunctions and apply disjunction to all of them. So the idea is as follows. Negations are applied first. So negations are applied directly to variables. It is not possible to negate conjunction or disjunction in this form. Negations are applied first, then conjunctions. Here we have a trivial conjunction of one member. And at last, we apply disjunction. It is also possible to have just one conjunction here. This is an informal description of a disjunctive normal form. As a circuit, it looks like the following. So we have some input variables, x1, x2, xn, and so on. We may apply negations to some of them, or to all of them, or to none of them. But anyway, negations are applied first. Also, it is possible to use our variables as is, without negation. Then, after that, we somehow take conjunctions of a few such terms. Then we take conjunctions. Here, this block stands for a conjunction of many arguments, something like that. While this is not optimal, but nevertheless, it is quite clear what I want to say. And then the results of these conjunctions are given to a final disjunction. Is this idea clear? Or do you need a formal definition? So a DNF is a circuit of special form, where first you apply negations, then conjunctions, and then disjunctions. So say no disjunction before conjunctions. No conjunction after disjunctions. No negation after conjunctions. Is this idea clear? Okay. And now, a theorem about DNF. Theorem 2. For every Boolean function of n arguments, there exists a circuit, a DNF circuit, that is a circuit of this form, of variables x1, xn, such that for every x, f of x is just the function our circuit computes. So our function is computable via a DNF. First of all, I give you an example. In fact, this example teaches us how one can construct such a DNF. So assume we are given with a function which is expressed via truth table, a table of all its values. If we have three variables, there will be 8 possible argument values. Please give me some values, whatever you want. Whatever you want. It is your choice. Give me some values. Ladies and gentlemen, are you present here? Apparently you are. So, what's the problem? Okay, why are you so passive? So let it be 0, 0, 1, 1, 0, 1, 0, 0. Why not? Something like that. So my idea is as follows. I can describe every unity of my function, that is every tuple where it takes 1, with a so-called elementary conjunction. What is an elementary conjunction? An elementary conjunction is a conjunction of variables or their negations. So this is called an elementary conjunction. An elementary conjunction. So I can, for every unity, I will construct an elementary conjunction. Which one? I will take x here with a negation. Why negate x? Because we have 0 here. Then I'll add y, but without negation, because here we have 1 for y. And I will negate z as well. So let us consider this conjunction. This conjunction uniquely describes this tuple. If we call this conjunction somewhere, I don't know, say, let's call it, let's call it phi. Let's call it phi of 0, 1, 0. Phi 0, 1, 0. What is the value of this function, or this formula, or this circuit? It is easy to see that it takes 1 if and only if x takes, not x, takes 1, that is x takes 0, y takes 1, and z takes 0. So if and only if sigma is just 0, 1, 0. Of course, when does it take 1? When not x takes 1, y takes 1, and not z takes 1. So this is the main idea. This formula, this expression or circuit, takes 1 if and only if it is given this very tuple. And similarly, I can consider all the other unities and construct similar conjunctions for them. Not x and y and z for this one. I have one more unity. And here I will put x and not y and z. Okay. So I have 3 elementary conjunctions, And if I take a disjunction of them, this will give us the same value as f. So let us just take the disjunction of all of those, and this will give us the same value as f. Why? Because f gives us 1 if and only if the input tuple is one of these three. Or equivalently, either this conjunction gives us 1, or this one, or this one. This is the main idea, and in fact, it provides us with an algorithm to construct a DNF given a truth table. Do we need a formal proof? Okay, let us give one. First of all, we need some notation to put this 0 into correspondence with negated variable, and 1 into correspondence with a variable without negation. So let us introduce the following symbol, where x is a variable, it is a syntactic object, it is a variable, and sigma is a Boolean value, either 0 or 1. X to the power sigma will be x if sigma is 1, and it will be not x if sigma is 0. So here, for example, I will have sigma to the power x to the power 0 and y to the power 1 and z to the power 0. That is exactly all this variables to the powers of their respective coordinates. Okay. You can treat it as a Boolean circuit. It either returns its input as is or it negates this. Clearly, the value it computes is 1 if and only if the value of x is sigma. It is easy to see that. So then, let U be the set of all such tuples where our function takes 1. It is either empty or not. So the first case is when U is empty. If U is empty, that means that our function is a constant 0. For every sigma, it is 0. How can we construct a circuit of this form which always gives us 0? It is very easy. We see that our function is just not x1 and x1. So we may construct such a circuit. All the other inputs are ignored. And here we have such a DNF for our function, not x and x. Okay. And the second case is when it is not empty. What should we do? It is quite easy. Let us consider D You may treat it as a formula or as a DNF. It is quite easy to see what does it mean. It will be a disjunction where we take phi sigma for every tuple, where we have unity for every tuple from U, where phi sigma is just x1 to the power sigma 1 and x2 to the power sigma 2 and so on, xn to the power sigma n. This very object. So here we have phi 0, 1, 0, x, the first variable to the power 0, the second one to the power 1, the last one to the power 0. Okay, clearly. When does this circuit, you can treat it as a circuit, when does it compute as 1? If and only if this gives us 1, this gives us 1, this gives us 1, that is every x equals its respective sigma, that is the input tuple equals our fixed sigma. Okay. So when does x over some input, when does d over some input x give us 1? It is a disjunction if and only if there exists at least one such sigma that this equals 1. So x equals one of our sigmas, that is input itself belongs to u, that is our function f at x returns 1. So this circuit D, it is of course a circuit, a DNF, because first we negate some variables, then group everything with conjunctions into our phi sigma, and then take a disjunction of all the resulting values. So it is a DNF, and this DNF returns 1 if and only if f returns 1. If two Boolean functions return 1 at exactly the same inputs, that means that they return 0 at exactly same inputs. That is, these two functions are equal to each other. What is CNF? A conjunctive normal form. It is a dual concept. It has quite a widespread idea in computer science, so please pay some attention to it. A conjunctive normal form. What is it? It is similar but dual. Here we have inputs x1, xn. Then we negate some of these inputs, or maybe all of them, and then we group the results into disjunctions. So first negations, then disjunctions, and finally a conjunction of the resulting values. So it is like DNF, but we change priorities of conjunction and disjunction. First disjunctions, then conjunctions. As an example, you can consider something like that. Not X or Z or not W and say not Z or Y and W or U or not X. Something like that. And in fact, as an exercise, you may prove that every Boolean function is expressible as a CNF. There exists a CNF. It is not unique. A CNF circuit such that C computes our function f. So every Boolean function is expressible in terms of a DNF or a CNF. But anyway, look, a DNF is a circuit over the basis of negation, conjunction, and disjunction. As every Boolean function is computable with such a circuit, we can immediately say that every Boolean function is computable from disjunction, conjunction, and negation. Every Boolean function. Or in other words, that means that the set of all Boolean functions is just the closure of these three. Interesting. Every Boolean function is a closure of these three. But we know that, say, disjunction is expressible in terms of conjunction and negation. Hence, this set is a subset of this one. And vice versa, of course. So we see that both these sets equal the set of all Boolean functions. And in fact, conjunction is also computable from disjunction and negation. Hence, this also equals this one. We see that this set is enough to obtain every Boolean function. Do we have any other such sets? Most interestingly, finite ones. Okay. Let us give a definition. A set Q of Boolean functions is called complete in T. That means if and only if its closure equals T. As an example, we see that this set and of course this one are complete. Do we have more complete sets? In fact, we have. Let us see a few more. First of all, I say that plus unity and conjunction, which you can treat as a multiplication, is also a complete set. Why is it so? In order to prove it, it is enough to express elements of one complete sets in terms of these ones. It is very easy now. Say negation belongs to the closure of this set. Why is it so? Because not x is just x plus 1, or formally 1 of x, but it doesn't matter. And of course, conjunction also belongs to this set. Hence, formally, we have this set being a subset of this one, whence its closure, which is T, is included into the closure of this set, but double closure is just the same as single closure. So we have that all these sets here are equal to T. Likewise, for example, you may say that implication and negation is also complete. Why is it so? As usual, it is enough to express every function from some set known to be complete. For example, it is enough to express, say, disjunction. But what is disjunction? X or Y, I say, X implication Y is just not X or Y. Hence, X or Y is just not X implies Y. Really, it is not X or Y, that is X or Y. So X or Y is just not X implies Y. So disjunction is computable from implication and negation. And of course, negation is computable this way. Hence, this set is also complete. Do we have a complete set that consists of one function? We have one. Let us recall the so-called Sheffer or Sheffer's stroke. I hope you remember this function. It takes two arguments and gives us the negated result of their conjunction, their negated conjunction. 0 and 0 gives us 1, 0 and 1, 1, 1, 0, 1, 1, 1, 0. So it equals the negated conjunction. In electronics, it is known as an AND, not AND, not AND. This function allows us to compute every other Boolean function. It is enough to have just such logical gates, such functions in our base. Let us see why. Clearly, first of all, we can obtain negation. Not x is x stroke x. Just look at these two lines. 0 stroke 0 is 1, and not 0 is, of course, 1. It is quite clear. And what about conjunction? As not and or Scheffer's stroke is a negated conjunction, we can obtain conjunction the following way. First of all, we apply our stroke and then negate the value. So it appears that this circuit computes as conjunction. So we see that both negation and conjunction are computable over just one function, this stroke. So this set of one function is complete. It is easy to see that negated disjunction shares the same property. It is known as Peirce arrow. As an exercise, you can consider the following Peirce arrow, which is negated disjunction. So proves that from this function you can obtain any Boolean function. But how can we generally judge whether a given set of Boolean functions is complete or not? We have a theorem. Unfortunately, we have not enough time to prove it, but nevertheless, this theorem alone is worth noting. It is the so-called post-completeness criterion. Post-completeness criterion. This criterion is as follows. For whatever set Q of Boolean functions, Q is complete in T, that is, every Boolean function is obtainable from Q, if and only Q, if and only if not every function in Q preserves 0, not every function in Q preserves 1, not every function in Q is self-dual, not every function in Q is monotonic, and not every function in Q is linear. So we need 5 functions, and maybe less than 5 if one function breaks more than one property here. But the only problematic thing here is checking whether a function is linear. How can we do that? Let me try to explain. In fact, every function can be expressed as a polynomial. So our last topic here is as follows. A polynomial representation of Boolean functions. Every function can be expressed as a polynomial, and in fact, you can do it just one way. And this is very important. theorem 4. For every Boolean function of n arguments, there exists a unique tuple of coefficients. Look, these coefficients are indexed with tuples. They're indexed with tuples. Of lengths n. So we have tuples, but here each tuple is of length 2 to the power n. Why is it so? For every tuple of zeros and ones, for every binary word, we have a coefficient. So there exists such a unique tuple that f of x equals a000 multiplied by 1, a1 000 multiplied by x1, a0100 x2, and so on. So what is the principle of naming these coefficients? Look, I will put unities here at the positions corresponding to the number of variables I take. If I have a monomial consisting of x1 and x2, I will take unities just on positions 1 and 1. And so on. And the last coefficient with indices 1, 1, 1, 1 corresponds to the monomial that includes every variable. How can we prove it? In fact, a formal proof requires some work, but the main idea is as follows. We can obtain a linear equation. We can obtain these coefficients from a system of linear equations. Are you familiar with systems of linear equations from your linear algebra course?
Yes.
Let us do it for an example. Let us take 3 variables. I'll call them x1, x2, and x3 in order to make this naming principle more explicit. So, for example, a101 will be a coefficient at which monomial? We have unities at positions number 1 and 3. So it will be a coefficient at x1 multiplied by x3. You know, this multiplication is just conjunction. Is it clear? Is it clear or not?
Yeah, it's clear.
Okay. I hope it is clear. In fact, presenting this stuff in all generality requires quite a good deal of work. So let us better stick to examples, but let us try to understand these examples. Please give me some values for this function, whatever you want. Whatever you want. Whatever you want. Let it be 1. 1, what else?
3.
1, 0, 1, 0, 0, 0, 1. For example. Okay. And what do I need? I need coefficients for such an equation. What is the right-hand side? I need how many coefficients? I need 8 coefficients which are indexed with these tuples. One, 1, 0, 1, 0, 1, 0, 1, 1, and the last 1, 1, 1. 8 coefficients, such that for every x, for every tuple of length 3, in this case, the following equation holds. F of x equals a0, 0 plus a1, 0, 0 x1 plus a0, 1, 0 x2 and so on. X1 multiplied by x2 x1 multiplied by x3 x2 x3 and the last one I want this hold for all possible values of x. But there are just 8 values of x here. That means that I have a finite system of equations. A finite system of linear equations. Let us write them down. The first equation is when I take f of 0, 0, 0. On the one hand, it is 1 according to my table. But on the other hand, what if I substitute 0, 0, 0 for all x's? What will I obtain from the right-hand side? Please tell me. It is important. What if I make all x's being 0? What will the result be? Everything except a0, 0 will be 0. I have multiplied a binary value by 0, so it is 0. Okay. My next equation, f1, 0, 0. From one hand, it is 0. And on the other hand, if x1 is 1 and all the other is 0, I will obtain a1, 0, 0. Is it clear? Please continue it. Please continue. If it is clear, please continue. What the this equals what? F of 0, 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, 1, 0. 0, look at the table. It is 0. And on the other hand, assume that x2 is 1 and every other x is 0. What will the right-hand side equal to? Isn't it obvious? I have just substituted this tuple here to the right-hand side. So x1 will be 1, x2 will be x1 will be 0, x2 will be 1, x3 will be 0. So what the right-hand side will be then? A0, 1, 0. Everything else is 0. Similarly, f of 0, 0, 1. According to the table, it is 1. According to the table, it is 1. And on the other hand, it is A00 plus A0, 1. Now let us consider tuples with two unities. 1, 1, 0, for example. From the table, we know that it is 0. And on the other hand, it is A00 plus. Here x1 and x2 equal 1. So we will have this one as x1 is 1. Plus this one, plus, of course, this coefficient. You may see that here we have all the coefficients which are less or equal than this tuple. For example, here we have 0, 0, 0, 1, 0, 0, 0, 1, 0, and 1, 1, 0 are all such tuples that are less or equal than this one. This is the main idea behind that. Okay, 1, 0, 1. According to the table, it must be 0. If I look at the right-hand side here and substitute 1 for x1 and for x3, while x2 is 0, what would I obtain? A00 plus A100 plus A001 plus A101. Two more equations. F of 0, 1, 1. On the one hand, it is 1. On the other hand, it is A00 plus A010 plus A001 plus A011. And the last one, F of 1, 1, 1. According to the table, it is 1. And on the other hand, it is the sum of all my coefficients, all of them. It is a lower triangle matrix. So you can prove it is not hard that this system has determinant 1. So it is solvable and there is exactly one solution. But can we solve it practically in this particular case? Let us try. So we already know that A00 is 1. That means that here we can replace it by 1 everywhere. As it is 1, so what is A1, 0, 0? 1 plus something equals 0. That means that this is also 1. 1 plus something is 0. So this is 1. 1 plus something is 1. So this is 0. Okay. So we have 1, 1, 1. 1 plus 1 plus 1 is 1. Plus x equals 0. So to obtain 0, we need evenly many unities. So it is also 1. Okay. Next. This is 1. This is 1. This is 0. 1 plus 1 plus x equals 0. What is x? X must be 0. This one. 1. A01 was 1. 0. 1 plus 1 plus 0 plus x equals 1. 0 plus x equals 1. So this must be 1. And the last one, 1. 1. 1, we know it already. 0. Next, 1. 0. 1. So here we have 5 unities whose sum is 1. 1 equals 1 plus x. So this must be 0. We have found all our variables by excluding them one by one from the system. Our standard method by Gauss. So what is the resulting equation is? Let us write it down. We see that our f must equal 1 plus x1 plus x2 no x3 plus x1 multiplied by x2 plus know this term plus x2 multiplied by x3. That's all. This is the coefficient. These are the coefficients for our function. You may check it if you want. If we have all zeros, we have 1. That's okay. Unity at x3 for x3. So it is 1. Unity for x2. 1 plus 1, 0. Okay. 0, 1, 1. 0, 1, 1. So we have 1 plus 1 plus 1. It must be 1. It is 1. 1, 0, 0. 1 plus 1 is 0. Okay. 1, 0, 1. 1 plus 1. That's all 0. It's okay. 1, 1, 0. 1 plus 1 plus 1 plus 1. 4 ones, 0. And finally, if we take all ones, we will obtain a sum of 5 unities, which is 1. Is this idea clear? So for every function, we have a unique polynomial representation. These polynomials, at least in Russia, are known as Zhegalkin polynomials for a Russian author who introduced them. Zhegalkin polynomials. Okay. So by solving such an equation, we can check every function, whether it is linear or not. Because a function is linear, if and only if it has no monomials of degree greater than 1. You know, a function is linear if and only if its monomial is of this form. So we have no, its polynomial is of this form. It has no monomials of degree 2 or more. As our very last point, let us check a system of functions, a set of functions for being complete with our post criterion. Let us consider an example. Let Q consist of, say, addition, implication, and what? And disjunction. Is it complete or not? How can we say whether it is complete? Practically, it is enough to check each our function for being an element of each of our closed sets: self-dual, monotonic, linear. Okay. What about plus? You know, in order to be complete, this set Q must be not included into every class P0, P1, S, M, L. So we need a function out of every class. Okay. What about plus? Does it preserve 0? 0 plus 0 is 0. So it preserves 0. Yes, that's not good. We need a function that doesn't preserve 0. What about implication? 0 implication, 0 is 1. Okay, it doesn't preserve 0. We have a function that doesn't preserve 0. Okay. P1, preserving unity. 1 plus 1 is 0, so it doesn't preserve unity. Okay, we have a function that doesn't preserve unity. Self-duality. You know, self-duality means that our function for every x, it returns the negated, its negated result at its negated input. What if we negate the input of plus? will it be negate the output? In fact, not. So is it true that x plus y always equals not x plus not y negated? Is it the case? No, it is not. Because 0 plus 1 is 1. And if I negate this inputs, I will obtain 1 plus 0, which is just 1, but not the negation of 1. So this function plus, gives us, in fact, identical values at 0, 1 and 0, 1 negated. So it is not self-dual. It is not self-dual. We have a function that doesn't preserve 0, which doesn't preserve 1, a function that is not self-dual. Do we have a not monotonic function? Yes, exactly. Addition is non-monotonic. We have already seen it. You know, addition is not monotonic. It takes 1 at 0, 1, but 0 at a greater tuple 1, 1. We have a non-monotonic, but of course addition is linear because it's polynomial. A polynomial is unique, you know. X plus y is just x plus y. It is a linear polynomial, while polynomial is unique. So it is not linear. It is linear. There is no way to express it otherwise as a polynomial. We need a non-polynomial function. But in fact, implication is non-polynomial. Non-linear. Why isn't it linear? If we obtain a polynomial for implication and this polynomial will not be linear, we will be sure that our function is not linear because the polynomial is unique. But what do we have for implication? It is easy to see that implication is just x conjunction y, or x multiplied by y plus x plus 1. Let us check it. When x is 0, it is 1. When x is 1, it gives us y. It gives us y. So if x is 1, it gives us 1 when y is 1 and 0 when y is 0. That is what we need from implication. And of course, this polynomial is nonlinear. The polynomial representation is unique. Hence, there is no way to make a linear polynomial for implication. Hence, implication doesn't belong to L, so it is non-linear. We see that this system of functions contains functions out of each of our critical classes, P0, P1, S, M, L. Hence, by Post's criterion, this system is complete. This system is complete, and moreover, we haven't even used disjunction. So even a smaller system is complete. Look, here we have established it by indirect methods. We haven't given any way to say express negation in terms of these functions. But can we? Can we, for example, express 1, express unity? Of course. Of course. This is enough to prove completeness according to the criterion, but can we do it more directly? Say, can we obtain negation? Of course, first of all, we obtain 1. 1 is x implication x, and negation is just x plus 1, that is x plus x implies x. It is always negation, and given negation, we can obtain disjunction. You know, x disjunction y is just not x imply y. That's it.